In this video, we solve problem 9.2.027 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. First of all, we're given this geometric series and we're asked to find the sum of the series. Then we're asked to use a graphing utility to find the indicated partial sum and then complete the table. And we're asked to round our answers to 4 decimal places. And then we're asked to use a graphing utility to graph the first 10 terms of the sequence of partial sums and the horizontal line representing the sum. First of all, I just want to point out that when they say find the sum of the series, usually that sum of the series does not have a subscript n on it. That's the nth partial sum. The sum of the series would typically be denoted by just s without a subscript at all. Now, if I expand this geometric series, when n equals 1, that's my first term. This is 7 times 0.9 raised to the 0th power, which is 1, plus 7 times 0.9 when n equals 2. That's going to be to the first, plus 7 times 0.9 squared. So this is what we get when n equals 1, 2, 3, and so on. So with that, we can see that the first term of the series is 7, and the common ratio, the number that we multiply by to get from term to term is 0.9. Since the absolute value of 0.9 is less than 1, we know this geometric series converges to its first term over 1 minus the common ratio, which is 0.9. 1 minus 0.9 is 0.1 or 1/10. So we've got 7 divided by 1/10. So that's 7 over 1 times 10 over 1 if we multiply by the reciprocal. And it turns out that the sum of the series is 70. So that goes right here. Now, we don't tend to use graphing utilities in my class. I don't teach you guys how to use graphing calculators, but we can find the nth partial sum of this series by using the nth partial sum formula. Here it is over here. If you had the sum as n goes from 0 to infinity of a times r to the n, so that's a plus ar all the way up to the a times r raised to the n minus 1 power. If you're adding all of those and you keep going, well, that's the entire series. The nth partial sum is just that expression right there. It's the sum of the first n terms. So there's actually a formula for this. And I think we proved it. We found this formula when we came up with the sum of a geometric series. This ends up being a times 1 minus r raised to the n, all divided by 1 minus r. And if we take the limit as n goes to infinity, if the absolute value of r is less than 1, this piece goes to 0, and we get a over 1 minus r, which is the sum of the series. But this is the formula for the nth partial sum. So I would just use a calculator to evaluate this expression at n equals 5, 10, 20, 50, and 100. It's actually not too difficult at all. So your a is 7. And then you're multiplying by 1 minus 0.9 raised to the 5th because n equals 5 here. And then you want to divide all of that by 1 minus r. That's 1 minus 0.9, which is 1/10. So you get 28.6657. That's what they wanted. They wanted us to round to 4 decimal places. Okay, let's do the same thing for n equals 10. So you have 7 times 1 minus 0.9 raised to the 10th. All divided by 0.1. So we get 45.5925. We'll do the same thing when n equals 2. 7 times 1 minus, oops, delete 1 minus r, that's 0.9, raised to the 20th, divided by 1 minus 0.9, which is 1/10. And we get 61.4896. And then for n equals 50 of 7 times 1 minus 0.9 raised to the 50th, divided by 1/10. And so you get 69.6392. And then when n equals 100, we have 7 times the quantity 1 minus 0.9 raised to the 100th. And we're dividing by 1/10 again. So you have 69.9981. So if we're looking at these nth partial sums, when n equals 5, we get this, n equals 10, we get this, 20, 50, 100. It seems like they're getting closer and closer to 70. And that's exactly the same result that we get when we compute the sum of the series. Then we're asked to use a graphing utility to graph the first 10 terms of the series. And you're given these graphs. I actually made a mistake and I accidentally wrote or drew the horizontal line y equals 70 here, but my whiteout has become not white. It's now translucent for some reason. So you can still see through that. But I think they have about y equals 0.8 is the horizontal line they've graphed here. So they say they want us to graph the first 10 terms of the sequence of partial sums. Remember that sequence of partial sums should be getting closer and closer to 70, right? And the horizontal line representing the sum, which is y equals 70. So right away, when I see this y equals 8 over here, I know it's not this one. And over here, as n goes to infinity, the sum of the series is supposed to approach this line. So that's definitely not the one. So it's either got to be this one or this one. But let's think about it. If we keep multiplying by this 0.9, then this plus this plus this is always going to be like a little bit more than the last term. So these guys, the individual term is approaching 0. But when I compare this plus this, that's the second partial sum, to this plus this plus this, that's the third partial sum. The third partial sum is a little bit more than the second partial sum. And how much more? It's this much more. So we're not going to have this pattern here where there are some partial sums that go down and then it goes up and then it goes down and then it goes up and then it goes down and then it goes up. This is what we might see if r happened to be negative sometimes, so that every time we were multiplying by r, the sign would alternate. So we would have a plus, minus, plus, minus, plus, minus. So then we would be, adding or subtracting and then adding, subtracting and then adding, subtracting and then adding. So this is a pattern that I might expect to see for a geometric series where r was negative, and so the nth term is alternating. But that's not what we have. The nth term is always positive. So the next partial sum is always a little bit more than the last. And in this picture, all of these points seem to be getting closer to y equals 70. So it's not that one because it has the wrong horizontal line representing the sum. It's not that one because those are going down and not up toward y equals 70. It's not this one because r would have to be alternating for this down, up pattern to happen. So it must be that one. Now, if you wanted to, you could compute s sub 1 through s sub 10 using this formula, and then just use something like desmos.com to graph all of those points. And you could write a little bit, I want to say code, but it's not really code, but you could write just like a little bit of math in desmos.com that would allow you to do this pretty easily. But I think we can just use process of elimination here. That can't be it. That can't be it because those are decreasing, and that can't be it because it has the wrong limit. So that one has to be the one. That's what I would recommend for this problem.